Hello everyone, a very good evening everyone. Just confirm me whether my voice is audible or not. Am I audible to everyone? Just confirm it once whether I am audible or not. Yeah, am I audible? Okay, so let's start this session. So a very good evening everyone. I welcome you all to the YouTube platform of IMS Gate Academy. Today we are going to conduct a session on structural analysis, and I'll make sure that you revise all the concepts using the numericals of the structural analysis. If I talk about structural analysis, my dear students, especially for gate examination, the level of question will be from easy to moderate level, right? The questions will not be difficult, the questions will not be lengthy. In fact, structural analysis is one of the most scoring area for gate examination. So if you have any question from structural analysis, try to solve it. Yes, sir. Thank you. Thank you so much. Okay. So try to solve it, approach it, and analyze it. And after that, you will surely get the answer. A very good evening, sir. Very good evening. Okay. So before we were going to start this session, I would like to just make few announcements. The first announcement is, my dear students, if you want to have the regular updates of all the PSU vacancies, you can join our Telegram group. The link is given in the description box. We post regular quizzes on our Telegram group, and also we post the schedule of our YouTube sessions, and you will get the PDF of our YouTube sessions in the Telegram group. Again, the link is given in the description box. The next announcement is from the courses that we offer at IMS Gate Academy. My dear students, we at IMS Gate Academy offer you with online program, offline program, hybrid program, and the self-learning program, where we give you around 800 plus hours of teaching content with live interaction and doubt solving. We provide you with theory and exercise book of all the technical subjects along with maths and aptitude, and along with that, in our exercise book, the questions are placed for like level 1, level 2 and level 3, so that even the student has the full-fledged idea where its preparation is going. Next thing, my dear students, we provide you with one-to-one mentoring sessions, 12 My Plan sessions, and these one-to-one mentoring sessions are like the game-changing sessions for the GATE aspirants. Over the years, we have seen that these mentoring sessions have helped the students to plan their content for the entire month, to plan their revision in the GATE journey, and also to keep them motivated throughout this hectic journey of 8 to 9 months of GATE preparation. Last but not the least, my dear students, we at IMS Gate Academy provide you with 130 plus tests. Now, this test series includes chapter test, subject test, multiple subject test, advanced subject test, and full-length mock test. And in all these tests, you can enjoy the varieties of multiple choice question, multiple select question, and the numerical answer type question. Okay. In this full-length mock test, you will even get the video solutions for it. So these are all the course details that we offer at IMS Gate Academy. So let me start the very beautiful session of structural analysis. The only thing that I need from your end, the only cooperation that I need from your end is just stay tuned till the last of this video. And I'll make sure to help you revise the full content of structural analysis in this session, right? So my dear students, structural analysis consists of degree of indeterminacy, then we have truss analysis, force method, displacement method, influence line diagram, arches and cables, and matrix method. This is one of the core syllabus of structural analysis from where we are seeing the regular questions. Okay. If I talk about structures, my dear students, we have three different varieties of structures. First one is the skeletal structures. You can see this framework, right? In this skeletal structure, you can see that you have a combination of columns along with the beams. So the structures for which only one dimension is predominating is termed as skeletal structure. In the entire analysis of structural analysis, we only deal with skeletal structures, right? Then the next variety of structure is your surface structure, where two dimensions are predominating. Example is the slab, where the length and width of the slab is predominating and the thickness is negligible with respect to the length and the width, right? The third variety of structure is known as the solid or massive structure. Now, these are such structures where all the three dimensions are predominating. Length, width, and height of the structures are predominating. Example is your dam. Any earth dam or any permanent dam that you construct is an example of a massive structure, right? in our structural analysis, we only deal with the skeletal structures. If I talk about skeletal structures, based on the type of joints, these skeletal structures are of two types, pin jointed structure and then we have the rigid jointed structure. This classification is based on the type of joints. It is based on the type of joints. Based on type of joint. So based on the type of joint, we have a pin jointed structure and a rigid jointed structure. Again, the pin jointed structure can be of two types. It can be a pin jointed plane frame or pin jointed space frame. The next can be, it can be a rigid jointed plane frame or a rigid jointed space frame. If we are talking about a structure in 2D, it will be a plane frame. If we talk about a structure in 3D, it will be a space frame. Chalo, moving on with this. Next, it is one of the very important thing in the analysis of structures, that which type of force system we are analyzing. So basically, we have four different types of force system. The first type of force system is coplanar concurrent force system, where only two equilibrium equations are there, right? Two equilibrium equations are present to analyze the structure. Then we have the non-coplanar, non-concurrent force system, where we have three set of equilibrium equations to analyze the structure. The third type of structure, the third type of force system can be non-coplanar plus non-concurrent force system, where we have again three equilibrium equations, and last one will be non-coplanar and non-concurrent force system. This is non-coplanar concurrent force system, where we have three set of equilibrium equations, and last, for non-coplanar non-concurrent force system, we have six set of equilibrium equations. First, what do you understand by structural analysis? Structural analysis is determining the unknown forces and the unknown deformations, right? If we need to determine the unknown forces and unknown deformations, the first thing that we need to understand is which type of structure we are analyzing. Whether we are analyzing a pin jointed plane frame or space frame, or a rigid jointed plane frame or space frame. Based on the type of structure, then we decide which type of force system is applicable. Whether it is a coplanar concurrent force system or any of these. The second thing is we need to decide which type of force system is applicable. Based on that, we can find out how many equilibrium equations we have. Okay. Now, next thing, my dear student, is if I talk about the unknowns, I should write here, in structural analysis, structural analysis is all about determining the unknowns. Determining the unknown forces and unknown deformations. Determining the unknown forces and unknown deformation is a part of your structural analysis. Now observe this. If I talk about unknown forces are determined using equilibrium equations. Unknown forces are determined using equilibrium equations. So, unknown forces are determined using equilibrium equations. For example, if there are x number of unknown forces and same x number of equilibrium equations are available to us to determine these unknown forces, then we say that the structure is a determinate structure. Then we say that the structure is a determinate structure. then we say that the structure is a determinate structure. But if the unknown forces are x and the available equilibrium equations are y such that your x is more than y, means your unknown forces are more than your unknown forces are more than your available equilibrium equations, then we require additional equations to determine all the unknown forces. In this case, when the unknown forces are more than number of available equilibrium equations, we say that the structure is an indeterminate structure. We say that the structure is an indeterminate structure. In order to find out all the unknown forces for an indeterminate structure, we need additional equations, and these additional equations are known as compatibility equations, which are formed by the boundary conditions. So, in order to analyze indeterminate structures, additional compatibility equations are required. Additional compatibility equations are required. Okay. So, first we need to determine whether the unknown forces can be determined using the unknown forces can be determined using the available equilibrium equations, or we require additional equations. So, for that, the first topic of discussion will be the degree of static indeterminacy. The degree of static indeterminacy tells us about how many unknown forces we have and how many available equilibrium equations we have. If the available equilibrium equations are less than the unknown forces, then the structure is said to be indeterminate. Then we need to determine how many extra equations we require. So that thing is determined using the degree of static indeterminacy. So the first topic of discussion is degree of static indeterminacy. So the extra number of equations required to analyze the structure apart from the equilibrium equations is termed as compatibility equations, and these extra number of equations are determined using degree of static indeterminacy. Degree of static indeterminacy is equals to total number of unknowns minus equilibrium equations. Degree of static indeterminacy includes degree of external indeterminacy plus degree of internal indeterminacy, where DSE is the external indeterminacy. Now I'll give you one very briefing about this. Degree of external indeterminacy, DSE. DSE will deal with the support reactions. DSE will deal with the support reaction. DSE will tell us that how many support reactions we have, how many extra equations we require for determining these support reactions. The second, degree of internal indeterminacy, DSI tells us about member forces, that how many redundant forces, member forces we have, and in order to find out these redundant member forces, how many extra equations we require. So the total degree of static indeterminacy comprises of degree of external indeterminacy and the degree of internal indeterminacy. Degree of external indeterminacy deals with the support reaction. Degree of internal indeterminacy deals with the unknown member forces, right? Now let's see for different types of frames. For pin jointed plane frame, degree of static indeterminacy is equals to DSE plus DSI. And I must tell you this, for a pin jointed plane frame, it is a coplanar non-concurrent force system. For a coplanar non-concurrent force system, we have three equilibrium equations. We have three equilibrium equations available to analyze it, right? So for this pin jointed plane frame, the degree of external indeterminacy, DSE, is equal to total number of unknown reactions. Total number of unknown reactions, I should write here, total number of unknown reactions minus equilibrium equations. So R is my unknown reactions and 3 is the number of equilibrium equations available to us. Next, for pin jointed plane frame, the degree of internal indeterminacy DSI is equal to m minus 2j plus 3. This is your degree of internal indeterminacy, right? So degree of external indeterminacy DSE is equal to r minus 3. Degree of internal indeterminacy is equal to m minus 2j plus 3. And when you add this, you will get degree of static indeterminacy, which is equal to DSE plus DSI. So this is equal to r minus 3 plus m minus 2j plus 3. So this will be m minus 2j plus r. So this is your degree of static indeterminacy. Now in the question, sometimes they ask you the external indeterminacy, sometimes they ask you the internal indeterminacy, sometimes they ask you the difference between the two indeterminacies, sometimes they ask you the degree of static indeterminacy. So accordingly, if you know these formulas, you can calculate any type of indeterminacy for the pin jointed plane frame, right? Chalo, let's see this. This is our first question of the day. Try this. I'll give you 3 minutes of time and I need quick answers from your end. Just go for it. You need to find both. In fact, all the three: degree of external indeterminacy, internal indeterminacy, and the total degree of static indeterminacy. So let's solve this question. So this is a truss given to you. For this, you need to find out the degree of static indeterminacy, right? So first of all, let's find out the degree of external indeterminacy, DSE. So DSE is equal to R minus 3. Now just take down the number of support reactions. So you have 2 support reactions here and 2 support reactions here. These are your hinge joints or hinge supports. 1, 2 here and 1, 2 support reactions here. So total number of support reactions are 4. So this is 4 minus 3. So degree of external indeterminacy is equal to 1. Now talking about the degree of internal indeterminacy, for that I require the number of members M. Okay. So let's count the number of members. This is my first member, second member. Then I have third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th. Then this is 12, 13, 14, 15, 16. Then this is 17 and 18. Total number of members are 18. Next, let's count the number of joints. So number of joints J is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Total number of joints are 11. So degree of internal indeterminacy DSI is equal to M minus 2J plus 3. So M is 18. 18 minus 2 into 11 plus 3. Just do this. So this will be 22 and this is 21. So 21 minus 22 will be minus 1. So when you add DSE and DSI, DSE plus DSI, this will come out as 1 minus 1 and this will be 0. So this is your degree of static indeterminacy for this truss, right? It's a determinate truss. Degree of static indeterminacy for this truss is equal to 0. Okay. Chalo, moving ahead with this. Try this question. Again, I'll give you 3 minutes of time. Just go for it. Go for it, go for it. Go for it, try this question. There's a pin jointed plane frame given to you. You need to find out the degree of static indeterminacy. let's solve this. So this is a question in which we need to calculate the degree of static indeterminacy, right? Okay, can you just observe this and tell me how many number of support reactions you can see in this question? How many number of support reactions you can see in this question? So you have a hinge support present here and you have a hinge support present here. So two support reactions over this support and two support reactions over this support. So total number of support reactions are 4. So the value of R is 4. So degree of external indeterminacy DSE is equal to R minus 3. So this is equal to 4 minus 3. So degree of external indeterminacy DSE is equal to 1. This is my degree of external indeterminacy. Now next is we need to calculate the degree of internal indeterminacy. For that, we require the number of members and number of joints. Please count the number of members. So number of members are how much? This is my first member, this is my second member, this is my third member, this is my fourth member, this one is fifth member, and this one is sixth member. Then I have this seventh member here. Then this is the eighth member, this is ninth, and this is 10th. Total number of members are 10, right? So these are the number of members. Members are 10. Next, number of joints. So 1, 2, 3, 4, 5 joints, right? This is not a joint. This is just an overlap. So total number of 5 joints. J is equal to 5. So degree of internal indeterminacy DSI is equal to M minus 2J plus 3. So M is 10 minus 2 into 10 plus 3. So degree of internal indeterminacy for this pin jointed plain truss is equal to 3. Sorry, this is how much? This number of joints are 5, not 10. So 2 into 5 minus 3 plus 3, sorry. So the degree of internal indeterminacy for this pin jointed plane frame is equal to 3. Right, so internal indeterminacy is 3, external indeterminacy is 1. So the total degree of static indeterminacy DS is equal to DSE plus DSI. So DSE is 1 and DSI is 3. So DS comes out to be 4. Degree of static indeterminacy for this pin jointed plane truss will be 4, right? So this is how you need to solve this question. This is one of the most asked question in different examination. So please go for it. Chalo, let's take the next question. This is the truss given to you. Okay, you need to find out the degree of static indeterminacy for this pin jointed truss. Go for it. Again, 3 minutes of time to you. Every question is important. Whatever questions we are discussing, each and every question is important. Go for it. Go for it. Go for it. Try it. Try it. Just 1 second. I was telling you that for a beam, right, if we know the external support reactions, we can determine the value of shear force, axial force and bending moment over any cross section of the beam. That's why beams are always internally determinate. We need to determine only degree of external indeterminacy for the beam. Now the degree of static indeterminacy for the beam is equal to total number of unknown reactions minus equilibrium equations minus force releases. These force releases are extra equations that we get for analyzing the structure, right? If we have an internal hinge over which M dash members are connected, then the total extra equations that we will get will be M dash minus 1. If we have a shear hinge, we will get one extra equation. If we have the internal link, we will get two extra equations. So like that, for different hybrid joints, we get extra equations to solve the beam, right? Chalo, let's solve this question. Try this one. Again, I have given you the timer, just go for it. Go for it. I want the answer from everyone. Can you answer this? What is the degree of static indeterminacy for the beam given below? Go for it, go for it. Go for it. It's a hardly 1 minute question, not more than that. And I'll tell you again, these varieties of question, you will get like 2 marks question in your GATE examination. Just go for it. Let's solve this. So you need to find out the degree of static indeterminacy for this beam, right? So this is my support. This is again my roller support and this is my hinge support. At this fixed support, we have 3 support reactions, 1, 2 and 3. At this roller support, I have only 1 support reaction, and at this hinge support, I have 2 support reaction. So total number of 3 plus 1, 4, 4 plus 2 is 6. So total number of support reactions are 6, right? The number of equations available to solve this beam are 3 right now. So degree of static indeterminacy is equal to degree of external indeterminacy plus degree of internal indeterminacy. For the beam, the degree of internal indeterminacy is always equal to 0. So this is equal to degree of external indeterminacy plus degree of internal indeterminacy, and here only I will write minus force releases, because hybrid joint is also present. Okay. Now degree of external indeterminacy is equal to R minus 3 minus force releases. Now you can see here there is one internal hinge present, and over this internal hinge 2 members are connected. So how many force releases are there? There is 1 extra equations available to you. Whenever 2 members are connected over the internal hinge, 1 extra equation you have. So number of force releases are 1. So this is equal to 6 minus 3 minus 1. So this will be how much? This will be equal to 2. So degree of static indeterminacy for this beam is equal to 2. Okay. This is how you need to go for it. Chalo. Let's do the another question. Try this one. Have 2 minutes of time. Just go for it. These are some of the very scoring areas of your structural analysis. Never miss a question asked from this segment. Go for it, go for it. Go for it. Please comment your answers. Go for it. Please comment your answers. Let's see this. Okay. So we need to determine the degree of static indeterminacy for this beam. So I have one fixed support, I have one roller support. Now this is your internal link. This is your link, right? And this is my hinge support. So I have three support reactions at the fixed support, 1, 2 and 3. I have one support reaction at my roller support and I have two support reaction at my hinge support. So total number of unknown reactions are equal to 3 plus 1, 4, 4 plus 2 is 6, right? The degree of static indeterminacy is equal to degree of external indeterminacy minus degree of, plus degree of internal indeterminacy minus force releases. This is the formula that we are using, and every time whenever you are solving any question for beams, for calculating the degree of static indeterminacy, please write down this. Every time you write down this, and then you write down that degree of internal indeterminacy for the beam is 0, right? Support reactions are 6. So degree of external indeterminacy is equal to R minus 3 minus force releases. Now this is an internal link. For an internal link, we get two extra equations. So number of force releases due to internal link is equal to 2. So degree of static indeterminacy for this beam will be equal to 6 minus 3 minus 2. So ds comes out as 1. This is your degree of static indeterminacy for this beam. ds is equal to 1, right? Chalo, moving ahead, try this question. You need to find out the degree of static indeterminacy for this beam, okay? Now observe this. Vertical loading is given to you. Vertical loading is given to you. So this is a vertical loading case. In the previous questions, nothing was given to you, no loading was given to you, nothing was mentioned. So it was a general loading case, right? It is a general loading case. Now here intentionally vertical load is given to you. So whenever vertical loading is given to you, you have to avoid all the horizontal reactions and all the horizontal equilibrium equations. Again, I am repeating myself. Whenever vertical loading case is given to you, you have to avoid all the horizontal reactions and you have to avoid all the horizontal equilibrium equations. So you can write down a note point for vertical loading case. For vertical loading case, horizontal reactions and horizontal equilibrium equations are avoided, or horizontal equilibrium equations are not counted. Right? So, whenever a vertical loading case is there, in the beam there will be only two equations of equilibrium available to you. So, I will write here available equilibrium equations are two. Available equilibrium equations are two, right? Now let's see the support reactions. So I have one vertical support reaction and the moment reaction here. I have to neglect the horizontal reaction. Similarly, I have one vertical support reaction here and I have one vertical support reaction here. Horizontal reaction here will be not counted, right? So total number of unknown reactions are 4. Number of unknown reactions are 4. So here degree of static indeterminacy is equal to DSE plus DSI minus force releases. Internal indeterminacy for the beam is 0. Since no hybrid joint is present, so force releases is also equal to 0. Now this degree of external indeterminacy will be equal to number of unknown reactions R minus available equilibrium equations. Now here the available equilibrium equations are 2. So ds will be equal to R minus 2. So R is equal to 4. R is equal to 4 and 4 minus 2. So degree of static indeterminacy for this beam is equal to 2. Now my dear students, you always keep a check. If nothing is mentioned, it's a general loading case. If nothing is mentioned, no loading is mentioned, nothing is mentioned specifically, it's a general loading case. But if any vertical load is applied, only and only vertical loads are acting over the beam, then it is a case of vertical loading, right? So even after knowing the concept, don't make these kind of silly mistakes. Please keep a check whether it's a general loading case or a vertical loading case. For the vertical loading case, you have to avoid all the horizontal reactions and the horizontal equilibrium equations, right? Chalo, moving on with this. Next you have the rigid jointed plane frames. In order to find out the degree of static indeterminacy for the rigid jointed plane frames, we have three methods. First of all, for the rigid jointed plane frames, we have both internal and external indeterminacy. Only for beams, internal indeterminacy will be 0. But whenever we have a rigid jointed plane frame, it will going to have both the unknown reactions and the unknown member forces. So degree of static indeterminacy for the rigid jointed plane frame is be equal to DSE plus DSI minus force releases. Again, these force releases will be due to the hybrid joints. So this is your first method. DSE will be equal to R minus 3. This DSE will be equal to R minus 3 and DSI this time will be equal to 3m minus 3j plus R. 3m minus 3j plus 3. 3m minus 3j plus 3. DSI will be equal to 3m minus 3j plus 3 and DSE is equals to R minus 3. So when you add these two, you will get ds is equals to 3m plus R minus 3j, right? Just remember this is just one of the way of solving the question. The next quicker method of solving the question is by counting the number of loops. So here C is the number of loops, number of closed loops present in the structure. So DSE, internal indeterminacy, will be equal to 3C and external indeterminacy will be equal to R minus 3. So when you add these two, ds will come out as R minus 3 plus C minus force releases if any hybrid joint is present. You have the third method here, okay. Just know the formula, I'll let you know. Means we will solve the question using all the three methods. So using the third method, ds is equal to 3c dash minus n minus force releases directly. 3c dash minus n minus force releases. That is your, or you can use this directly. ds is equal to, here you can avoid these force releases. I tell you how you can avoid this. We can count everything in n. So 3c dash minus n is the degree of static indeterminacy, where c dash is the number of cuts required to make the free cantilevers. Okay, and n is the number of restraints required to stabilize the cantilever. Chalo, let's solve this question. Try this question. You have 3 minutes of time, just go for it. We will solve it using all the three methods. Just go for it. Let's solve this question. Okay. Now first using method 1, which is one of the lengthiest method. First method. Just count the number of members. So you have 1, 2, then this is 3, 4, then this is 5, 6, then this is 7, 8, 9 and 10 members. So number of members are 10. Number of joints will be 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of 9 joints you have. Next is the number of support reactions are. So here we have 3 support reactions, 1, then 2 and the moment reaction 3. Here we have 1 support reaction and again we have 3 support reactions here, 1, 2 and 3. So total number of support reactions will be 3 plus 3, 6 plus 1, 7. So total number of support reactions are 7, right? So degree of external indeterminacy, DSE, is equal to R minus 3. So this is equal to 7 minus 3. So 7 minus 3 is 4, right? Degree of static indeterminacy, DS, is equal to DSE plus DSI minus force releases. Minus force releases, right? Now when you add these two, this will be 3m minus 3j plus R minus force releases. Minus force releases. Now one thing I would like to bring to your notice, whenever we are talking about the degree of static indeterminacy, right? We do not count these hybrid joints in this value of j. We only count the rigid joints, okay? When we talk about the degree of static indeterminacy for frames, we only count the rigid joints. We don't count these hybrid joints, okay? Now next. So 3m, number of members are 10. So this is 3 into 10 minus number of joints are 9. So 3 into 9 plus unknown forces. Unknown forces are 7 minus force releases. Now this is the axial shear hinge. So one force release from here. One force release from here. This is the vertical shear hinge. So one force release from here and one force release from here. So total number of 4 force releases. So minus 4. So this is your degree of static indeterminacy for this rigid jointed plane frame. So this will be 30. 30 minus 27 will be 3. 3 plus 7 will be 10 and 10 minus 4 will be 6. So DS for this frame comes out to be 6. So this is one of the method to solve this, right? Now let's check method number 2. This is your axial shear hinge here. This is your vertical shear hinge here. Sorry, axial shear hinge here, vertical shear hinge here. Again, axial shear hinge here and a vertical shear hinge here. This is your frame, right? Now you have to just count the number of closed loops. So this is my first closed loop. This is my first closed loop and this is my second closed loop. So number of closed loops, C. Number of closed loops is equal to 2, right? Support reactions R is 7. So DSE is equal to R minus 3 plus 3C minus force releases. Right? Now again R is equal to 7. So R is 7. So this is equal to 7 minus 3 plus 3 into 2 minus force releases are 4. Just count this. So 3 minus 7 will be 4. So 4 and 4 will cancel out and you have 3 into 2, 6 directly. So DS, this is DS, not DSE. Degree of static indeterminacy DS is equal to 6. Directly in one line, just counting the number of closed loops, you have found out the degree of static indeterminacy for this beam, sorry, for this frame. Okay, so this is your method number 2 to determine the degree of static indeterminacy. Now let's check the method number 3. Method number 3 for determining the degree of static indeterminacy for this frame goes like this. This is your vertical shear hinge. This is your axial shear hinge. Right. Now method number 3 is, in method number 3, we have to cut this frame so that these 3 supports should form individual cantilever segments. Right. We have to cut this frame in such a way that these 3 supports should have individual cantilever segments. Observe this. So how many cuts are required? Observe this very carefully. How many cuts are required? If I give one cut here, another cut here, right? Then if I give one cut here, another cut here, this will be my individual cantilever segment. This will be my first individual cantilever segment like this. This will be my first individual cantilever segment. And I think if you apply the force, it can withstand that force. It will undergo some deformation, but when you remove the force, this cantilever segment will regain its original shape and size, right? So this is one of the stable cantilever segment. So right now, how many cuts are required? So C dash, number of cuts required to have individual cantilever segments, is equal to 4. Now next, come to this middle cantilever segment. This middle cantilever segment is like this. This is your middle cantilever segment. Here it contains the axial shear hinge like this. And this is the horizontal shear hinge. This is your axial shear hinge, right? And here you have a roller support. Now, first of all, if you apply any force over this middle cantilever segment, it can very easily displace. So first we have to restrict this displacement. For that, we have to provide one horizontal restraint here like this. We have to provide one horizontal restraint like this. Second, it can also undergo rotation. So we have to also provide the moment restraint over this support. So only over this support, 2 restraints are required in order to make this cantilever stable. Now come to this axial shear hinge, right? This portion of the axial shear hinge is unstable. It will going to fall if you just cut this segment from here. So this segment of the axial shear hinge requires one vertical restraint. Similarly, this portion of the horizontal shear hinge, requires one horizontal restraint like this, right? So how many horizontal restraint? One horizontal restraint here, another horizontal restraint here. So total number of restraints required to stabilize this middle cantilever portion is 1, 2, 3 and 4, right? No restraint was required in the first portion, but second cantilever requires 4 restraint. Now observe this third one. This is your third cantilever. Now this third cantilever contains horizontal shear hinge like this with this portion and axial shear hinge like this. Okay. Now when you apply the load over this cantilever, this fixed support will going to be provide restraining forces or reactions in order to stabilize the cantilever. But when you observe this axial shear hinge, it requires one vertical restraint here, and this horizontal shear hinge requires one horizontal restraint here, right? So the total number of restraints required to stabilize all the portion of the cantilever will be 1, 2, 3, 4, 5 and 6. So the value of n is 6, right? So degree of static indeterminacy using method number 3 is equal to 3c dash minus n, where c dash is the number of cuts. So this is 3 into 4 minus number of restraints required 6. So from here the value of ds comes out as 6. And this is your method number 3 to solve the same question. So in the examination, it is always advised to go with method 2 or method 3 if you have a question from the rigid frame, right? So I hope you got this. Chalo, let's move ahead. Try this question. I'll give you 2 minutes of time. Try to go for this. Go for it. Please comment your answers. Please comment your answers. Go for it. Go for it. Go for it. Let's solve this question. So you need to find out the degree of static indeterminacy for this rigid jointed plane frame, right? Two hybrid joints are given to you, two internal hinges are given to you, right? So again, by method number 1. By method number 1. First count down how many members are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 members are there. So M is equal to 12. Number of joints J. Number of joints are 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of 9 joints. How many support reactions? So 2 here, 1 here and 1 here. So total number of 4 support reactions. So degree of static indeterminacy is equal to 3m minus 3j plus r minus force releases. minus force releases, right? So 3 into 12 minus 3 into 9 plus support reactions are 4. Now force releases are the extra equation. Over this internal hinge, two members are there. So one extra equation you will get from here. Over this internal hinge, again two members are there. So one extra equations you will get from here. So total number of two force releases you have. So this is equal to 36 minus 27. That will be 9. 9 plus 4 is 13. 13 minus 2 will be 11. So the degree of static indeterminacy for this frame is equal to 11. This is using method number 1. Now method number 2 says you just need to count down the number of closed loops. So the value of C in method number 2. So you have one closed loop here, you have one closed loop here, you have one closed loop here, and you have one closed loop here. So total number of 4 closed loops you have. So C is equal to 4. So ds is equal to R minus 3 plus 3C minus force releases. So R is equal to 4, 4 minus 3 plus 3 into 4 minus force releases is 2. So 4 minus 3 will be 1 and 1 plus 12 will be 13. 13 minus 2 will be 11. So from here the degree of static indeterminacy again comes out as 11. Now coming to method number 3. Method 3 is ds is equal to 3c dash minus n, right? So you need to find out the number of cuts. So how many cuts are required to form 3 cantilevers? So one cut here, one cut here, one cut here. Then you have one cut here, one, like this. So you require total of 6 cuts to have 3 independent or individual cantilever components. So C dash is equal to 6. Now how many restraints you require? So here you require one moment restraint in the first portion of the cantilever. In the second portion of the cantilever, you require one horizontal force restraint and the moment restraint. And in this pin joint, you require one moment restraint like this, right? So in the second part or in the second cantilever, you require 1, 2 and 3 force restraints. In the third portion of the cantilever, you require one moment restraint here. You require one horizontal force here, horizontal restraint and a moment restraint here. So total number of restraints required are 1, 2, 3, 4, 5, 6 and 7. So the value of n is 7. Okay. So this will be ds is equal to 3 into 6 minus 7. So 3 6 is 18, 18 minus 7 is 11 again, right? So using all the 3 methods, I have solved this question. So any of the method you can use in the examination. I will always advise my student to go with method number 2 or method number 3. Specifically method number 2 is good. Chalo, try this question. Try this question, have 2 minutes of time and I want your answers quickly. Get me the degree of static indeterminacy for this. Get me the degree of static indeterminacy for this frame. Chalo, I'll go with this. I'll solve this question using method number 3. First of all, how many cuts required? So you require 1, 2, 3, 4, 5, 6. Total number of cuts required C dash is equal to 6. Now talking about number of force restraints required to stabilize the 3 cantilevers. So in the first cantilever, you require one moment restraint here, right? In the second portion of the cantilever, you require one horizontal restraint and a moment restraint over this support. Then there are 4 members meeting over this joint, right? So this member is a stable member, but this member and this member are unstable members, and since they are connected due to internal hinge, they require one moment restraint here, they require one moment restraint here, and they require one moment restraint here in order to stabilize the structure. So 3 restraints are required over this internal hinge. Now talking about this internal hinge, again one restraint is required and another restraint is required in order to stabilize these 2 members. Then over this roller support, again one horizontal restraint and a moment restraint is required. So total number of restraint required to stabilize all the 3 cantilevers are 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So total number of restraints required are 10. So degree of static indeterminacy will be equal to 3c dash minus n, and this is equal to 3 into 6 minus 10. So 3 6 is 18. 18 minus 10, which comes out as 8. So degree of static indeterminacy for this rigid jointed plane frame is equal to 8, right? Next, solve next one. So next is your degree of static indeterminacy for the rigid jointed space frame. Now again the questions framed from this area are very less, but still if a question comes, you should know that the degree of static indeterminacy is equal to degree of external indeterminacy plus degree of internal indeterminacy minus force releases. Degree of external indeterminacy is equal to R minus 6 because 6 support reactions are available to you in rigid jointed space frame. Rigid jointed space frame is a non-coplanar, non-concurrent force system. So 6 equilibrium equations are available to you. So ds is equals to R minus 6. Next, degree of internal indeterminacy is equal to 6m minus 6j plus 6, right? So when you add these two, you will get the total degree of static indeterminacy, which will be equal to 6m plus R minus 6j minus force releases. Minus force releases. So if you get any question in the examination, you can use these equations and to determine the degree of static indeterminacy, okay? So this is the portion about degree of static indeterminacy, okay? The other methods could be for rigid jointed space frame. The method 2 could be if you have counted the number of closed loops. So there the degree of static indeterminacy will be equal to R minus 6 plus 6c this time, 6c. If you are using method number 3, then degree of static indeterminacy will be equal to 6c dash minus n, only 6c dash minus n, right? This will be equal to 6c dash minus n, simple. Hardly you will get any question in the examination. Now talking about one of the very important aspect, that is stability of the structure. My dear student, in order to analyze the stability of the structure, you have to analyze both externally and internally. If the structure has to be externally stable, then the reaction forces should not be parallel to each other. Means all the reaction forces should not be parallel to each other. If there are three reactions acting, then if all the three reactions are parallel to each other, like this case, here the support reactions are parallel to each other like this. So if you apply any horizontal force over this structure, this structure will undergo rigid body translation, which makes this structure as unstable. So whenever all the support reactions are parallel to each other, then the structure is a unstable structure. So this is my unstable structure. This is my unstable structure. Next, if the support reactions are collinear like this, if your support reactions are collinear like this, if your support reactions are collinear, again your structure will be unstable. So there are only two conditions to check for the external instability. Structure will be externally unstable if the support reactions are concurrent, means if they are meeting at a point. Second, if the support reactions are parallel to each other. Now observe this structure. For this structure, I have one support reaction like this and another support reaction like this, right? And this support reaction is like this. So these three support reactions are neither parallel nor concurrent, hence this is your stable structure. This is your stable structure. Similarly, for this structure, you have one support reaction like this, another like this, and a moment reaction like this. So one reaction like this, it is like this, and the another one like this, right? Since all the support reactions are neither concurrent nor coplanar, is nor parallel, therefore this structure is externally stable. Okay, externally stable. Externally stable, right? For checking the internal stability, the first criteria is you need to check what is the degree of static indeterminacy. If degree of static indeterminacy is greater than or equal to 0, then we say that the structure is internally stable. Then we say that the structure is internally stable. Then we say that the structure is internally stable. But I must tell you, there will be few structures for which you need to check the other criteria as well, right? This is not the sole criteria to check the internal instability. This is just one of the criteria to check the internal instability, right? If the degree of static indeterminacy is equal to or greater than 0, then we say that the structure is internally stable. But we cannot say that with 100% confidence. You need to check, for example, if you get a truss like this. If you get a truss like this, for example, you got a truss like this. You got a truss like this. Now for this truss, the degree of internal indeterminacy is greater than or equal to 0, right? For this truss, the degree of internal indeterminacy is greater than degree of static indeterminacy for this truss is greater than or equal to 0. So just by observing this ds for this truss, I cannot say that this truss is stable or not. The second criteria to check the internal instability is if these member forces are concurrent. If these member forces are concurrent at one point, then also this truss will become unstable. Reason is, if you apply any force like this internal triangle will going to rotate. This internal triangle will going to rotate like this. this internal triangle will going to rotate like this, and this causes the internal instability. This causes the internal instability, right? So if you are checking for the internal instability of the structure, first thing is you need to check for the degree of static indeterminacy. But degree of static indeterminacy is not the sole criteria to check whether the structure is internally unstable or not, right? The another criteria is you need to check whether the member forces are concurrent at one point or not. If the member forces are concurrent at one point, then we say that the structure will be internally indeterminate. So this is your internally indeterminate structure. This is internally unstable structure, sorry. This is internally unstable structure. Okay. Chalo, moving on to the next. Then we have the degree of kinematic indeterminacy or the degree of freedom, right? First of all, for the hinge support, the degree of freedom is 1. For the roller support, the degree of freedom is 2. Okay, for hinge support, it can only rotate. So degree of freedom is 1. For roller support, it can also move along the surface and it can also rotate, right? The member can rotate and move along the surface. Therefore, the degree of freedom for roller support is 2. For guided roller support, the degree of freedom is equal to 1. Guided roller support can only move along the surface along which you have provided the guided roller support. Degree of freedom for fixed support is equal to 0. Fixed support, the member which is connected with the fixed support can neither move in the horizontal direction, nor it can move in the vertical direction, nor it can rotate. Next, for axial shear hinge, vertical shear hinge and internal hinge, the degree of freedom is equal to 4. For a pin jointed space frame, the degree of freedom is 2. For pin jointed plane frame, the degree of freedom is 2. For pin jointed space frame, the degree of freedom is 3. For rigid jointed plane frame, the degree of freedom is 3. For rigid jointed space frame, the degree of freedom is 6. Let's check with the questions. Okay, so these are the direct formulas of kinematic indeterminacy. For the pin jointed plane frame, kinematic indeterminacy is equals to 2j minus r. For pin jointed space frame, this is equal to 3j minus r. If the members are inextensible, then the degree of kinematic indeterminacy is equal to 3j minus r plus extra degree of freedom due to hybrid joints. If members are inextensible, then the degree of kinematic indeterminacy is equals to 3j minus r minus m. Here these m is the number of inextensible members plus extra degree of freedom due to hybrid joints. For inextensible members for frames, degree of kinematic indeterminacy is equal to 3j minus r plus extra degree of freedom due to hybrid joints. For inextensible members, the degree of kinematic indeterminacy will be 3j minus r minus m plus extra degree of freedom. So these are some of the formulas to calculate the kinematic indeterminacy. Please go for this question. I'll give you just 1 minute of time. Okay. So for this beam is a rigid jointed plane frame. For a rigid joint, there are 3 degrees of freedom. For a rigid joint, there is 1 horizontal, vertical and the rotational degree of freedom like this. So for every rigid joint, I have 3 degrees of freedom, 1, 2 and 3 like this. I have 3 degree of freedom, 1, 2 and 3 like this, right? Every rigid joint has 3 degree of freedom. Now these degree of freedom will be restricted by these support reactions. So degree of freedom or degree of kinematic indeterminacy for this beam is equal to number of joints are 3. So this is equal to 3j minus r. So number of joints are 3. So this will be 3 into 3 minus support reactions. So 3 support reactions here, 1 here and 1 here. So total number of 5 support reactions. So this is equal to 9 minus 5, which is equal to 4. Okay. You can observe this vertical support reaction will not allow this vertical movement. Again, this vertical support reaction will not allow this vertical movement. Similarly, all the 3 support reactions over the fixed support will not allow the horizontal, vertical and the rotational movement. That is why the degree of kinematic indeterminacy for beams is equal to 3j minus r, right? There is no hybrid joint, so we will not talk about the extra equations. Chalo, go for this question. So this is your truss. For this truss, you need to find out the degree of kinematic indeterminacy. This is the truss given to you. This is not beam, this is a truss given to you. You need to find out the degree of kinematic indeterminacy. Go for it. So first of all, for every pin joint in plane frame, the 2 degree of freedom is there, horizontal and vertical movement. For every joint, degree of freedom is 2, 1 and 2, 1 and 2 like this. Then here also this is 1 and this is 2. Here also it will be 1 and it will be 2. For every joint, your degree of kinematic indeterminacy is always governed by the type of joint, whether it is a rigid joint or a pin joint. For a pin joint, every joint has 2 degree of freedom. Now when you observe this support, this vertical reaction will not allow this vertical movement. Again, this vertical reaction will not allow this vertical movement. This vertical and horizontal reaction will not allow this horizontal and vertical movement. So either you can count the arrows directly and report the degree of kinematic indeterminacy. That will be 1, 2, 3, 4, 5, 6, 7 and 8. You can count the arrows directly and you can report the degree of kinematic indeterminacy just by observing the arrow, or you can use the formula. So according to the formula, degree of kinematic indeterminacy is equal to 2j, because every joint has 2 degree of freedom, 2j minus r. So number of joints is equal to 1, 2, 3, 4, 5, 6. Total number of 6 joints. So 2 into 6 minus number of support reactions, 1, 2, 3 and 4. So this is equal to how much? This is 12 minus 4. So 12 minus 4 is 8. I think the same number we have counted, 2, 4, 6, 7 and 8. Degree of freedom for this truss is 8, right? Chalo, go for the next question. This is again here truss. You need to find out the degree of kinematic indeterminacy for this pin jointed truss. You need to find out the degree of kinematic indeterminacy for this truss, right? Again, we can go with the same method. For every pin joint, the degree of freedom is 2. For every pin joint, the degree of freedom is 2. For every pin joint, the degree of freedom is 2. 1, 2, 1, 2 and 1, 2. Again 1 and 2. For every pin joint, the degree of freedom is 2. So this is 1 and then this is 2. Again this is 1 and this is 2. Again this is 1 and this is 2. Now again I'll start from this. This vertical support reaction will not allow this vertical movement. Then coming to this, the vertical and the horizontal support reaction will not allow the vertical and the horizontal movement. So either you can count these arrows directly and report the degree of kinematic indeterminacy. So this will be 2, 4, 6, 8, 10, 12 and plus 1, 13. So either you count the arrows and you write down dk is equal to 13, or you can also use the formula. So if you are using the formula, first you need the number of joints. So how many joints? 1, 2, 3, 4, 5, 6, 7, 8. So total number of 8 joints. How many support reactions? 2 here and 1 there. So total number of support reactions are 3. So dk is equal to 2j minus r. So this is equal to 2 into 8 minus 3. So this is 16 minus 3, which is again 13. I think the same value we have calculated. So either you can use the formula or you can directly count the number of arrows. Okay. Chalo. Next, try this one. Now this is with a hybrid joint. I want you to give it a try. Just have it for 1 minute. Go for it. So you need to find out the degree of kinematic indeterminacy. Okay, let's solve this. Okay. So first of all, this is your rigid jointed frame, right? This is your rigid jointed frame. This is your rigid jointed frame, right? First of all, for every rigid joint, there are 3 degrees of freedom, 1, 2 and 3. For every rigid joint, there are 3 degrees of freedom like this, 1, 2 and 3. For every rigid joint, you have 1, 2 and 3 degree of freedom. Again, 1, 2 and 3 degree of freedom. 1, 2 and 3 degree of freedom. Again, 1, 2 and 3 degree of freedom like this, right? Axial shear hinge has 4 degree of freedom. It has 1 delta x1. Again, you have delta x2. Delta x1 will be for this portion. Delta x2 will be for this portion. It has 1 vertical deflection and 1 rotation. So like that, your axial shear hinge has 4 degree of freedom. Similarly, your internal hinge has 1 rotation here, has another rotation here, free rotation. You have 1 horizontal displacement and 1 vertical displacement. So again, your internal hinge has 4 degree of freedom. Now just observe the support. This fixed support will not allow this vertical movement, this horizontal movement and this rotational movement. Similarly, this shear hinge will not allow this vertical and the horizontal movement because of the reactions at this internal hinge. Your roller support will not allow this vertical movement, right? So either you can count this directly and report the degree of kinematic indeterminacy. So let's do this. So this is equal to 3. 3 plus 4 is 7. 7 plus 3 is 10. 10 plus 4 is 14. 14 plus 3 is 17. 17 plus 2 is 19. And 19 plus 1 is 20. So from here the value of dk is 20. Now use the formula. So dk is equal to, for a rigid jointed plane frame, this is equal to 3j minus r plus extra degree of freedom due to hybrid joints, right? So here you have two hybrid joints. So in this, how many joints are present? So whenever you are calculating the degree of kinematic indeterminacy, hybrid joints are also counted under the count of j, number of joints. So total number of joints will be 1, 2, 3, 4, 5, 6, 7, 8. Total number of joints are 8. Total number of joints are 8. How many support reactions? So 3, 4, 5, 6. Total number of support reactions are 6. Okay, next. How many extra degree of freedom? So every rigid joint has 3 degree of freedom, right? This is also we have considered as a rigid joint, right? So as a rigid joint, this is having 3 degree of freedom, but 1 extra degree of freedom. So apart from 3, this joint has 1 extra degree of freedom. Similarly, this joint also has 1 extra degree of freedom. So number of extra degree of freedom will be 1 plus 1, 2. Total number of 2 extra degree of freedom we have. So dk is equal to 3j, j is 8, minus r, which is 6, plus 2 extra degree of freedom. Just count this, 24, 24, 26. 26 minus 6 is 20. 26 minus 6 is 20, right? So either you can use this arrow method or you can use the formula. Whichever is convenient to you, you can just go for it. Chalo, try this one. You need to find out the degree of kinematic indeterminacy for this frame. So every rigid joint has 3 degree of kinematic indeterminacy, 1, 2 and 3 like this. Again 1, 2 and 3 like this. Again 1, 2 and 3 like this. Again, this is your internal hinge. Now this internal hinge is connected with 3 members. So these 3 members will have independent rotation, 1, 2 and 3. Then this internal hinge will have horizontal displacement and will going to have vertical displacement. So total of 5 degree of freedom is available with this internal hinge. Similarly, at this rigid joint, you have 1, 2 and 3 free degree of freedom. Here also 1, 2 and 3 degree of freedom. Now this internal hinge has 1 rotation, 2 rotation, 3 displacement and 4th one is the horizontal displacement at this internal hinge. At this rigid joint, you have 1, 2 and 3 displacements like this. Here also you have 1, 2 and 3 displacements like this, right? Now observe the, okay, here also you have 1, 2 and 3 displacements like this, degree of freedom like this. Now this support will not allow any horizontal movement, any vertical movement, any rotation. This hinge support will not allow any vertical and the horizontal movement, it will allow the rotation. This fixed support will again not allow any horizontal, vertical movement and the rotation, right? So you can also count it directly. So the degree of freedom for this rigid jointed plane frame will be 5 plus 3, 8. 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 1, 15. 15 plus 4 is 19. 19 plus 3 is 22 and 22 plus 3 is 25. 22 plus 3 is 25. So from the diagram, this is 25. Now you can also use the formula. So dk is equal to 3j minus r plus extra degree of freedom due to hybrid joint. So number of joints, how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total number of 10 joints. How many support reactions? So 3 here, 2 here and 3 here. So that will be 8. So number of support reactions are 8. How many extra equations you have? So here the degree of freedom is 5. So apart from 3, you have 2 extra equations here. 2 extra equations here and 1 extra degree of freedom here. Not equation. 2 extra degree of freedom here and 1 extra degree of freedom here. So total of 3 extra degree of freedom you have. So dk is equal to 3 into 10 minus 8 plus 3 extra degree of freedom. Please count this. So this will be 30, 30 minus 8. 30 minus 8 is 22, 22 plus 3 is 25. So dk comes out to be 25. dk is 25, right? So this is your degree of kinematic indeterminacy. Just try this one also. You need to find out the degree of kinematic indeterminacy. Now this is very simple. For every rigid joint you have 3. So this is your kinematic indeterminacy for, this is your truss, right? Here it is not written, this is your truss. This is your truss given to you, and for this truss you need to find out the degree of kinematic indeterminacy. So for truss, for every pin joint you have 2 degree of freedom, 1, 2, 1, 2 like this, then you have 1, 2 like this, you have 1, 2 like this, you have 1, 2 like this, you have 1, 2 like this. Then you have 1 and 2 like this. You have 1 and 2 like this, right? This is your truss, not a frame. Right now it is a truss. For a truss you need to calculate the degree of kinematic indeterminacy. So for this truss, this and this movement will not be allowed. This movement and this movement will not be allowed. So total number of 2, 4, 6, 8, 10, 12. So dk will be equal to 12. Okay, if this is a truss. For frame it will be different. Now for a truss, this is your degree of freedom. Okay. Chalo, have this. You can have this directly, right? Try this. You can take the screenshot for this. Just try this question. I'll give you just 2 minutes of time. Go for it. It's a very important question again. It's a frame. Rigid jointed plane frame. First of all, my dear students, I have just cross-checked this. This is not your truss, this is your frame. First of all, this is your frame. For frame, you have 3 degree of freedom for every rigid joint. 1, 2 and 3 like this. This is 1, 2 and 3 like this. Again this will be 1, 2 and 3 like this. This will be 1, 2 and 3 like this. Again this will be 1, 2 and 3 like this. This will be again 1, 2 and 3 like this, right? Now this hinge support will not allow this movement and this movement, vertical and horizontal. Similarly, this hinge support will not allow vertical and horizontal movement. So you can just count down the degree of kinematic indeterminacy. So you have 1, then this is 3, 4, 4 plus 3, 7, 7 plus 3 is 10, 10 plus 10, 10 plus 10 is 20. So dk for this frame is 20. dk for this frame is 20. It is not a truss, it is a frame, okay. Chalo, for this one you calculate. For this one you calculate. For this one, the degree of kinematic indeterminacy for the beam shown in the figure is, right, you can just take the screenshot, you can, okay. So this is our degree of static and kinematic indeterminacy. Now, my dear students, there are assumptions, certain assumptions, and using those assumptions, we analyze the truss, determinate trusses. First assumptions are members are perfectly straight, individual members are connected with frictionless hinges. Next, loads are acting only at the joint, self-weight is neglected, members are only under the action of axial forces. I think you know this. We have 3 methods to determine the forces in the members. Zero force members, then you have method of joints, and then you have method of sections. I hope you have learned all these methods in your engineering mechanics, right? So I just want to give you some questions. You need to find out how many zero force members are there. So in order to find out zero force members, there are 3 conditions. First one, if 2 members are meeting at a joint, if this is a truss joint, if 2 members are meeting and no external load is acting over the joint, then force in both the members will be zero force. Second, if 3 members are meeting at a joint such that 2 members are collinear and no external load is acting over the joint, then force in the third member will be zero force, right? Next, if 2 members are meeting at a joint such that the external load F is in line with one of the member force or is in line with one of the member, then force in the second member will be zero force, right? So just keep these 3 conditions in your mind and you can identify the zero force member. So first one is, if I start from this joint contains these 2 members in line and this will be your zero force member. Again, when you come to this joint, just forget this member and observe this member, this third member is not in line with these 2 members. So this is a zero force member. Again, when you observe this joint contains this member which is not in line with the other 2 member. So this is your zero force member. Then come to this joint. This joint has this member which is not in line with the other 2 members. So this is your zero force member. Okay. Now come to this joint. This joint has this member which is not in line with the other 2 members. So this is your zero force member. Next, you come to this joint. This joint contains this member which is not in line with the other 2 members. So this is your zero force member. Again, when you observe this joint contains this member which is not in line with the other 2 members. So this is your zero force member. Okay. So when you come to this joint, now this joint contains 1 member and 2 members. So we cannot say anything about any of the zero force member present at this joint, right? At this joint, external load is acting. So again, we cannot say this. At this joint also external load is acting. So we cannot say anything. But when you observe this joint, this is a zero force member. This is a zero force member. So we are left with only this member which is not in line with the other 2 members. So this is also your zero force member, right? So how many zero force member? 1, 2, 3, 4, 5, 6, 7 and 8. So total number of zero force members which are present in the truss are 8. Okay. Chalo. Next one is this. You need to find out the forces in the members. You can use any of the methods to find out the forces. Okay. Now, when you observe this joint C, this external load W is in line with the member AC. So this force in the second member will be zero force, right? Similarly, if you take the summation of moment about B equal to 0, this is your length L. If you take summation of moment about B equal to 0, then you have this external load and here you have the support reaction. The value of horizontal support reaction will be 0 because there is no horizontal load acting over the members, or there is no external load, no horizontal load present over the truss, right? Therefore, the horizontal force is equal to 0. Now, if you take the summation of moment about point B equal to 0, you will find that you have the anti-clockwise moment due to this support reaction at A. So that will be equal to VA into L. And then due to this external load, there will be the anti-clockwise movement. Value will be minus W into L. So your VA is equal to W. VA is equal to W. And when you write down summation of vertical forces equal to 0, you will have VA plus VB. VA plus VB is equal to W. So VA is W plus VB is equal to W. So from here the value of VB comes out to be 0. So if VB is 0, member force BC is 0. Again you observe this joint B. No external load is acting over this joint B. So force in both the members will be 0 force. Will be 0 force, right? You can take joint C, and when you write down the summation of vertical forces, force in the member CA will come out as W, and this force will be compressive in nature, right? So like this you can solve for the trusses. You can solve for the trusses, right? Now here also you need to find out the member forces. Now for finding the member forces, first of all, always go for the 0 force member, so that you can reduce the number of unknown members. So next is, when you observe this joint C, there is no external load acting over this joint C. Therefore, both the members meeting at this joint C will be 0 force members. So this is my 0 force members, right? Next, this is my horizontal reaction at D. So this is HD. This is my horizontal reaction at A. So this is HA. And this is my vertical reaction at A, VA. Let me apply this horizontal reaction at D like this. This is my horizontal reaction at D, and this is equal to HD, right? Take the summation of moment about this point A equal to 0. So when you write down summation of moment about A equal to 0, you will going to have the clockwise moment due to this external load, and the value will be W into L. So you have W into L, external load, right? The second moment will be due to this horizontal reaction, and the value will be HD into L again. So it will be an anti-clockwise moment, so minus HD into L, and this will be equal to 0. So from here the value of HD comes out to be W. The value of HD comes out to be W, right? Now next, you take the summation of horizontal forces equal to 0. From there you can calculate the value of HA. So summation of horizontal forces equal to 0. So minus HD plus HA minus HD plus HA is equal to 0. So HD is W. So this is minus W plus HA is equal to 0. So from here the value of HA comes out as W. Value of HA comes out as W, right? You got the value of HA. Now you can take the summation of vertical forces equal to 0. So this VA will be equal to W. VA will be equal to W. This vertical reaction at A, VA will be equal to W, right? When you observe this joint A, you will get, when you write down the summation of horizontal forces equal to 0, this HA is W. So the member force in this member will be also equal to W. So force in the member AB will be equal to W. And when you take the summation of vertical forces equal to 0, the force in the member AD will be also equal to W, right? Now, when you take the summation of vertical forces equal to 0, this is your 45 degrees. So this FDB sin 45 is equal to W. So this force in the member FDB will be equal to W root 2, and this will be tensile in nature, right? So again, this is a part of your engineering mechanics. You read there also about trusses, right? So this is about your trusses. You can calculate the member forces using method of sections and method of joints, right? So this is all for the day. I hope you have learned so many new things today, and I just wish you all the best for your GATE examination. Again, you can join our Telegram group. The link is given in the description box. You can avail any of our program. Again, the links are given in the description box. So thank you so much. This is all for today. Have a very great night ahead.